Okay, welcome everyone. We're very happy to have the second talk for the morning session of the first day by Nitu Kitchloo from Johns Hopkins, who's going to tell us about symmetry breaking and homotopy types for link homologies. Nitu, please.
Chum, can you guys hear me? Can you all hear me? Okay, great. I want to thank Hisham for organizing this. It's a great group of friends so far away from home. And it was very tenuous for me to get here, but he persisted, and here I am. So it's good to see all of you. I haven't seen most of you in so long. The only difference now is that you have a few more gray hair. Otherwise, you're all the same. I certainly do. So the other reason I want to thank Hisham is I have a mathematical story to say, but this being partly a physics workshop, I had to think very hard to organize my mostly incoherent thoughts into physical ideas. So now they are mildly incoherent, but I also haven't slept for 48 hours, barely slept. So I am also incoherent. So I figured I'd do both together and pitch my incoherent physical ideas in a state of lack of coherence. Okay, so let me first get to my way of thinking of how to pitch the mathematics. And then the second half of my talk, I'll give you the actual mathematics, which is rigorous. The first part is sort of the ideas, the physical context in which I think these mathematical ideas will fit. So, let's say we have an ND gauge theory. So you don't have to know, if you don't already know, what an ND gauge theory is. The whole point is the basic fields, so our maps from spacetime into the stack BG, which I think of as point mod mod G. Okay, so we're working with a ND gauge theory, which has basic fields, which are maps into this stack, which classifies principal G bundles. So now let me give a name. Let F be the compactification of this theory on S1. So what are the basic fields of F? Of F are maps from n-1d spacetime into the stack maps from S1 into point mod mod G, which is the stack G mod mod G with the conjugation action, the adjoint action. So when I compactify my ND gauge theory, the basic fields are going to be maps from your spacetime into the stack G mod mod G. So let's just think about this guy for a moment. The stack G mod mod G. And so let me assume something about G here. I'm going to assume G is compact, connected, fixed maximal torus, T inside G, and root datum. So just fix some basic roots, co-roots, Cartan, that kind of information for G right from the get-go. So now let's think about this stack G mod mod G under the conjugation action. The coarse moduli is a space, it's a polytope called the Weyl alcove. So let me draw a picture. It's a picture like this. So it's a polytope. Its dimension is the rank of G. And this is the coarse moduli. So sitting above this are objects with automorphisms. And this is just your coarse moduli. So let me indicate how the stabilizers of objects sitting over various faces of this polytope are. So sitting above this vertex here are objects that are fixed by G. Inside here, in the interior, are objects that are fixed whose stabilizer is exactly the maximal torus. If you take a face, so let's take this face, it's corresponds to objects whose stabilizers are what I'll write Gi, and Gi, so this is a codimension 1 face. Gi is called the rank 1 levy. So basically what Gi is, it's a rank 1 semi-simple group extended by an n-1 torus, where n is the, sorry, not n, rank. So Gi is the extension of a rank 1 semi-simple group by a rank r-1 torus. So let's say G has rank R. Okay, so what I want to do now is to point out that the data of this picture allows us to construct a point mod G gauge theory. This is corresponding to the interior. With defects, so domain walls for codimension 1 faces, defects for higher codimension faces. So this whole picture you should think of as a gauge theory with structure group G, and then for each domain wall, for each codimension 1 face, you get a domain wall between the theory and itself. We'll call that theory F by, so the point mod T gauge theory so this is just abuse of notation. I just don't want to introduce too much notation. So I want to think of this picture giving rise to the following structure. I want to think of it as giving rise to a gauge theory with structure group T, and each time you cross a domain wall, you're breaking your, so the domain wall will correspond to GI bundles, and you're breaking the symmetry as you cross a domain wall. So corresponding to GI is breaking down to T. Okay, so this is just sort of a context. You don't have to really understand all details if you are not familiar with this language, but what I want you to take away from this is that what I can do is think of this picture as something, a field theory built out of principal T bundles, and every time you see a wall, you're thinking of principal T bundles, this field theory for principal T bundles somehow admitting a symmetry that corresponds to a codimension 1 wall that is indexed by this rank 1 Levy subgroup GI. Okay, any questions? So the next thing I want to do is to pitch the mathematical content of what I'm going to prove, or at least express, and then put it in this picture. All right. So let me state the main results. So I decided to state the main results so that if I don't get to them at the end, at least they're out there. So you... Sure. Sure. Yeah. No worries. Okay, so here are the main results. So I'll write box BRG denote the conjugacy classes of elements in the Artin braid group so BRG will stand for the Artin braid group. So remember, G has root datum, so I can describe, I can write down a presentation for the Artin braid group. So that's going to be denoted by BRG, and this box indicates conjugacy classes. So given beta belonging to the braid group of G, so we denote L of beta to be its conjugacy class. So the notation here is to suggest that in the case where G is an AN, is UN or SUN, then the conjugacy classes of braid groups with a slight technicality correspond to links. If you have a braid, so the classical braid can be thought of as an element in the AN type braid group. And if you think of a braid and you close the braid, so this is the picture for the AN type. If you have a braid, so this is an element beta. If you think you could think of its conjugacy class as what you get when you close a braid. In this case, it's not terribly interesting. So this indexes links. So L stand for links. So we'll denote conjugacy classes in the Artin braid groups by this symbol, though that symbol only represents links in the AN case. Okay. So given beta, let this guy be its conjugacy class. So we will describe a G equivariant filtered homotopy type, which I'll write BS for broken symmetry, L of beta. Okay, what can you say about this filtered homotopy type? So BS L of beta will be an invariant of L of beta. So it'll only depend on its conjugacy class up to a notion of quasi-equivalence of filtered spectra. Okay, so if you don't know what spectra are, don't worry about it. Just think of spaces. So I'm going to describe a filtered homotopy type. That filtered homotopy type is going to be a link invariant. In other words, it's going to be an invariant of a conjugacy class up to a notion of equivalence. So invariance up to a notion of equivalence, which I call quasi-equivalence. And I will maybe mention a word about that equivalence at a later point. BS L of beta will record symmetry breaking of my theory F along S1. So I take a circle and I break my symmetry on that circle in this theory that I'm calling F. So that combinatorial structure will be recorded by this homotopy type. So in particular, from this description, so each point of this space will be a certain symmetry breaking on a circle. So for each point on that space, what I can get is defect data for my theory F. So one gets a family of denoted by F S1 L beta parametrized over broken symmetry L beta. So note, if F was fully extended, well, let's say the original gauge theory was fully extended, was of a fully extended ND-TQFT. So remember, we started off with an ND-TQFT. Let's say it was fully extended. We started off with ND field theory. Let's say it was a TQFT, and let's say it was fully extended. Then what this is, then a family of objects in an n-2 category. So since we're breaking symmetry over a circle, and remember F started off as being the compactification already of an ND theory, so this data gives you objects in an n-2 category that are parametrized by points in the space of broken symmetries. So that's the structure you will get. You'll get a parametrized family over these spaces that I'm telling you exist. Let me tell you more about these spaces. So if G was UR, so let's say G was UR. So this is now a specialization. Then I can calculate the equivariant cohomology of the space of broken symmetries of the link. Then this, as a filtered object, calculates the Kovanov-Rozansky triply graded link homology. Of L of beta. Remember, in the AN case, which is the relevant case over here, these conjugacy classes gives rise to links. And so now I have this filtered equivariant space. I can calculate its equivariant cohomology. It's a filtered object. That filtered object gives rise to a bi-graded object. Cohomology has its own grading, and then a filtered object gives rise to another grading. That filtered object ends up having a third grading. And as such, it calculates the Kovanov-Rozansky triply graded link homology. So this is a categorification of the Homfly PT polynomial, if you know what that is. Where here, what is R? R equals number of strands. I want to point out a little bit more. I mean, you can ask that you have these link homologies, but there's many more. There's a whole family, the SLN link homologies. And in some sense, the SL infinity link homology is this. There's a notion that there's a family, and in the infinite case, you get this Kovanov-Rosansky homology, but then there is SL2, which is the Kovanov homology, and then so on, later on, SL3, SL4, known as SLN link homologies. Can you recover those? And the answer is yes. The point here is BS L of beta maps to the stack G mod mod G almost by construction. This guy will map to this stack. So this guy will give you a local system where you can calculate twisted cohomology of this in any cohomology theory that has a twisting by this. So this implies one can calculate twisted cohomology of BS L beta with respect to any cohomology theory with twisting by G mod mod G add. So here G is a unitary group. So twisted K theory, there's a twisting of singular cohomology too. And by choosing suitable twistings, one gets SLK link homology for all K. So you can get all these link homologies as specializations of this one homotopy type. So it's a homotopy type for Kovanov homology. And it fits as this data of symmetry breaking if you were to start off with any ND gauge theory with that structure group. It's only in the case of AN that you get link invariance, but in general what you will get will be somehow conjugacy invariant for the Artin-Braid group of G. Okay, so
Sorry.
yes, yeah, sure.
I try to figure out in the case you start with singular homology with this twist. Sorry. If you consider singular homology with those twisted coefficient,
Yes.
does this mean that you can represent this using certain G flat connections or something like this?
So you mean the cohomology using G flat connections?
Yeah. I mean, how do you? What is the setup for the
Perfect. Good question. So I'll get to it in maybe 10 minutes. I will give you exactly how to construct singular cohomology as a twisted cohomology with those twistings. So that's exactly the kind of question I would like to answer before I get to the end. Good. So I have 40 more minutes.
No, at least 30 minutes.
I started at 10:40.
Yeah, so we still have 35 minutes.
Okay, good. 40 minutes. Am I generally coherent up to this point? Oh, okay, good. I don't know if you have the feeling, sometimes you think you're perfectly coherent, and then a day goes by, and then you go back to your ideas, and they make no sense. I don't know. It happens to me all the time. Okay. Okay, so I told you that there is such a space. It exists. It's a filtered G homotopy type. It records symmetry breaking for some field theory over a circle. And I said the cohomology of this homotopy type recovers all the link invariance in the AN case that we can think of, unless, of course, you're working with more refined invariants like colored link invariants and stuff like that. Okay, so let me construct this. It's not a terribly hard construction. It's the following. Okay, so remember that my G came with root datum. So it had a maximal torus and it had root datum. So its Artin-Braid group has canonical generators. So let sigma 1, sigma 2, sigma r So here G is arbitrary. It's not AN type for now. So let these guys be the standard generators. So R is the rank of G. If it's semi-simple, otherwise it's the semi-simple rank. So I'll work with elements of the braid group that are positive. In other words, they have positive exponents. They're written as words in terms of these generators with positive exponents. This is just a technical artifact. If I were to work with words in the art and braid group that had negative exponents, then I'd have to replace my spaces with spectra, Thom spectra. And I suspect that not everybody is familiar with the language of equivariant spectra. So I'm just going to set that aside and just work with positive exponents so that I can work in the world of spaces as opposed to spectra. So it's just an artifact. So let's say I'm given a multi-index. Let's say I1, I2, up through IS. Let sigma sub I be the braid word. Sigma I1, sigma I2, sigma IS. So these could be repeated. The corresponding braid word. Okay. So let me define B sub I. So I'm going to define a space B sub I as follows. G crossed over T, GI1 crossed over T, GI2 crossed over T. Remember these GI1, GI2, these correspond to codimension 1 walls of your vial alcove. So these are subgroups of semisimple rank 1 inside G. And they all contain the maximal torus. So I'm looking at this space, and then I'm giving it a T action. The T action here is just the left-right action here. So the T action in the inside is the one you would expect. There's a T action outside. The T action on GI1 crossed over T GIS is, so let me show you what it is. It's T acting on a tuple G1, G2, GS. It's conjugation on the first and last factor. So it's TG1, and then you just put G2, G3, and the moment you get to the end, you put an inverse. So here's my G space. Okay, this is not broken symmetries. This is B sub I. So this is my definition of B sub I, and I'm going to use this collection of B sub I to construct my space, which I'm calling BS as a filtered space. But what is this space? So let me give it a meaning, a geometric meaning in terms of symmetry breaking. So what is this space? So B sub I is the moduli space of G connections on S1 with S marked points. Let's call them X1, X2, up to XS, such that the structure group is reduced to T at each marked point. The holonomy of the connection between X sub I and X sub I plus 1 is in G sub I. So here's the picture. I have connections which are G connections on a circle. This is x1, this is x2, x3, all the way up to xs. The structure group is T at every point. And here, holonomy. So as you move from this point to this point in GI1, so my indexing should have been better. Maybe I should call this J plus 1, I sub j. GI1, here the holonomy in GI2, etc. So you have these connections, and your structure group is T at all these points. As you move from one to the other, you pick up holonomy, but the holonomy is constrained by these subgroups that correspond to symmetry breaking. So you want to think of the circle moving in this vial alcove. It's crossing a codimension 1 wall here. It's crossing another codimension 1 wall here. It's crossing another codimension 1 wall here. So it's sitting in the interior here, and then it's sort of moving to a wall, crossing the wall, reaching this point, crossing the wall. So this is symmetry breaking data for the picture that I drew with the vial alcove in the beginning. So if you think of this data, it's a stack. That stack is represented by this G space. So I'll let you figure that out as homework. That this space is precisely this data. I want to point out one thing, that this space still has a residual T action on the right. T is an abelian group, so this T is acting by conjugation, but it commutes with the right action. Okay? So I can quotient out the right T action. So maybe I should put a note here. Bi mod T, so this is the right T action. So what is this space? I'm okay with them now, right? G crossed over T, GI1 crossed over T, GI2 crossed over T, and G I sub S. So this is sort of like a Bott-Samuelson variety. This corresponds to the moduli of G connections on intervals with S. So just replace this circle by an interval, and you get the moduli space is represented by Bi mod T. Maybe I should call it a name, Bi mod T. Well, let's call that AI. And notice that Bi over AI is a principal T bundle. Okay. All right, so let me make a couple more observations to get eventually to this filtered space that I want. The first observation is if J is a subset of I, so if J is a subset of I, so J is just a multi-index that is a sub-collection of I, then there B sub j sits inside B sub I by setting G sub I equals the identity if I does not belong to J. So just think of B sub j as those GIs for those I's that lie in J, and then you want to make it sit inside GI, just set those indices which don't lie in J as the identity. So that gives you an inclusion. So what does this correspond to physically? This corresponds to transparent domain walls. So remember, you have these domain walls that correspond to the Levy subgroups GI that are codimension 1 faces between the two T-gauge theories, the codimension 1 face. But notice GI also contains the maximal torus. So you can have a connection that has holonomy inside the maximal torus. So it doesn't give you anything new. There is nothing that happens that's already not there to begin with in the T gauge theory. So these are called transparent defects or transparent domain walls. So the inclusion B sub j sitting in sub B sub I corresponds to transparent. Transparent is a thing, okay? I mean, I just didn't make it up. There's something called transparent domain walls. Defects. Along intervals that correspond to indices of I not in J. So in that picture that I had, there would be some of these indices, there will be intervals that don't exist in J, and for those intervals, you're just putting the identity element, and so you're thinking of passing a domain wall that's transparent, is not visible along those intervals. You have a reduction of the structure group to T here, the holonomial lies in T. You don't see anything new. Your field theory doesn't detect a symmetry as you pass that interval, so it's transparent. Okay, so here's my space BS. So definition. Define the filtered space BS as, so B sub I is going to be the beginning space. Then I'm going to have BS L beta 1. So this is the zeroth filtration, first filtration, all the way up to Sth filtration. S corresponds to the length of the word. We had the word that had S generators in it. So that's this S. And what is this guy? So I'm beginning with BI, which has all defects, transparent and all. Every defect is in there, all crossing all domain walls, transparent or not. This guy is going to be the one where I'm pinching out all transparent defects. So BS L of beta is the cone. So I'm going to write it like this. Sorry, we've been calling it B, not BS. So these are all, defects along all intervals. So all possible transparent defects that map into this. This is a union. But really, if you want to describe this homotopically, you should take a colimit, but I'm not going to do that. Yeah?
I'm sorry, I think I missed, what is BI of L beta?
Sorry, I didn't say L beta, but I just mean BI. Each of the B's depend on a braid word. So just everything in the background, there is a braid word, right? There's an index I, so that corresponds to a braid word. So the cone on this is what I mean by S. So the top space is obtained from this by pinching out all transparent defects. So you're taking this and getting rid of all possible transparent defects, killing them. So you can call these strict broken symmetries. Strict meaning you're taking broken symmetries and killing out anything transparent in it. So strict broken symmetries. And then how would you make it into a filtered spectrum where this is S? Here you would just kill those, you'd kill transparent defects that are transparent at 1 point. Then you would kill stuff that are transparent at 2 points, 3 points. And here you're killing everything transparent at all points, right? So this would be, you're taking J has only one index where it's transparent, okay? Does that make sense? So J is all of I save one index. In the next step, you would take J to be everything save 2 elements in I. and so on and so forth. So it's just the cardinality of J that keeps increasing as you move from here. There is no J here. You've killed no transparent defects. And here you've killed all transparent defects. So you just interpolate to get a filtered object as you kill more and more transparent defects. Okay? So BS L beta J, or maybe I shouldn't call it J, K corresponds to transparent defects along K intervals. Okay, so I'm not going to spell it out what it means as a cone, but it is what you'd expect it to be. You can write it as a colimit over a subcategory of the poset category of subsets of I. Okay, all right. Question?
Can you phrase this in terms of superficial sense?
You can phrase this in as a colimit. So you have a functor, let's call that B dot from 2 to the I to G top, and it sends J over to B sub J. And this thing has a terminal object, obviously, I. So you can think of this as being the colimit over the subcategory of this functor of all proper subsets. And this is the terminal object, and this is just the cone of that. And then you could think of, you can take the subset of take the subcategory of all subsets of I, but of cardinality starting with nothing and cardinality being the whole, all subsets, proper subsets, and taking colimits over those subcategories, and they would correspond to the pinchings for all of these. So I don't want to spell that out, but it's kind of clear what I'm trying to do over here. Okay. So that's my space of broken symmetries. All right. So let me give you a few theorems that I alluded to in the beginning about the cohomology of this space and about the space itself. First theorem. So we're getting to the mathematics now. Is an invariant of L beta lies in the conjugacy classes of the Art and Braid group. As a G equivariant filtered stable homotopy type up to quasi-equivalence. So this is the time for me to tell you what quasi-equivalence means, of course, because if I don't explain it to you, this is a vacuous statement. It's just like two of them are equivalent if they're just, I don't know, equivalent to a point or something. So let me tell you what quasi-equivalence means. So quasi-equivalence literally is given the following way. So let me describe some context. If one has a filtered spectrum, let's call it A dot. So don't worry if you don't understand spectrum, just think of the space. You have a filtered space, A dot, so dot stands for the filtration. Then one gets a chain complex in the stable homotopy category. We'll write it the associated graded of A dot, which is so by AK mod AK minus 1, I just mean the cone of the map from AK minus 1 into AK. A dot is a filtered object, so there's a map from AK minus 1 to AK. Take the cone on that, and I call that this space. just, this is my notation for the cone, and you desuspend it k times because you're working in the stable category. So there is a desuspension. And this collection of spectra is in fact a chain complex in the stable homotopy category. There are maps from one to the next, and the composite maps are trivial. So something is quasi, so when I say this is a link invariant up to quasi-equivalence, I mean I kill all filtered spectra for which this is null homotopic. So null homotopic, a chain complex is null homotopic if you have a map back so that the composite map is an equivalence, right? Just what you would do in usual chain complexes, if you have chain complex, you say a chain complex is null homotopic if you have backward maps so that DH plus HD is an isomorphism, right? DH plus HD is a self-map now at each level, and if that self-map is an isomorphism, you say that that chain complex is null homotopic. So I can make that statement here, that any filtered spectrum is null homotopic if this object is null homotopic. So quasi-equivalence is the equivalence relation on filtered spectra that sets A dot to be trivial if the associated gradient of A dot is null homotopic. Okay? So in particular, if I had a map of filtered objects whose fiber was null homotopic, that map would be an equivalence, up to quasi-equivalence. It would be an equivalence in this. So in that sense, this guy is an invariant. In other words, if I had two braids and I looked at the conjugacy, if they had the same conjugacy class, then I could get a zigzag between the constructions of one braid and the other braid so that all the fibers are null homotopic. Okay, so you can connect one to the other. So that's the theorem. Okay, so now let's specialize to, so this is the theorem for general G. Let's specialize to the case of G equals AN, or UN, the unitary group, so that I can get myself down to the link homologies. Okay, so now set G as UR. So note one has a spectral sequence, and you have a filtered object, you always get a spectral sequence that converges to the limit or the union of the filtered objects. E1 this is a filtered object. This is the limiting case of the filtered object. It's the union of things. This is the associated gradients. You always have a spectral sequence whose E1 term is this, and E infinity term is this. So theorem, all EQ stages of the spectral sequence are link invariants of L of beta. Remember, L of beta in the case of the classical case of AN represents a link in R3. So our link invariance of this guy for Q bigger than equal to 2. So not E1, but after you take the first differential, you're going to get E2. That's a link invariant. E3 is a link invariant. E4 is a link invariant, and so on. E2 is isomorphic to Kovanov-Rozensky triply graded link homology. So there is an invariant, like I said earlier, Kovano-Rosansky triple Gaussian homology. That invariant is recovered as the E2 term of this spectral sequence. So now let me point out how you get all the SLNs, and that will get to the question that was asked about how singular cohomology can be made into a twisted cohomology theory. So first, BI supports a map to G mod G add. So this is true for any G, even though we're only working with the AN case. And so how does this map go? It just sends G, comma, G1, G2, GS. This goes over to G, G1, G2, GS, G inverse. So this is an equivariant map you can check. This map corresponds to the fact that you're breaking your symmetry at k points, but you can always take the composite. You could just take your connection and go all the way around the circle, come back to x1. So it's just composing all the possible holonomies along the way, all the way around. So this is that map. So this is compatible under Bj sitting inside Bi. So in other words, if you map both, this diagram commutes. So what you get is a local system over the filtered space. So this gives rise to a local system over. Remember, this was built out of these inclusions. So now, if G equals UN, UR, consider HG, and by this I mean you take singular cohomology and you smash it with BU. As an 8 BU, think of BU as an 8 space. So this is an 8 space. So this must be infinity space even. So this is an equivariant ring spectrum. So you're taking this. BU is loops on SU, right? Bot periodicity. And there's a map from UR to S, well, UR to U. That's obviously a map of A infinity spaces, so it's a map of groups. There is a projection to SU that is also, in the limiting case, a map of groups. So you can think of, and this can be made equivariant. And so you can think of this as being loops BU, or B of SU equals, well, anyway, BU. Sorry. Sorry, I got that wrong. I want this to be the group, so I loops on SU. That's right. So this I want to think of B of loops on SU. Which is B. Did I get that right? Yes. Okay. So this is, so that tells you that you get, exactly. So what that says is that you get, this is a classifying space of loops SU, which is BU. And therefore, I can think of this guy here as a spectrum which has a twisting by this, which induces a twisting by this. Therefore, this says, so, right? So you can think of this as the group. Think of this as a group, G, not G. Think of this as a, so I'm taking a spectrum, smashing it with a group. To say that it has a twisting, I just want to map to B of that group, right? And that's what this map SU is. So by smashing HG with this, I get a twisting by UR mod the conjugation action. So this is the answer to the question. Script HG, which is HG smashed with BU plus, has a twisting by UR mod UR conjugation for all R. Okay, so notice that HG of a point is just, it's a polynomial algebra on these variables in even degree. If we set BI, let's say BK to be 1 for BK to be 1 for I equals K and 0 for I not equal to K. So I set all but 1 equal to 1, and I look at the specialization. So this is the twisted cohomology. Then this is SLK, link homology of L beta. So slightly incoherent here, but let me repeat what I was saying. I took singular equivariant cohomology and I made it twisted with respect to this local system where G is UR using this map. UR maps to U maps to SU, and I think of SU as the classifying space of loops SU, but loops SU is BU, right? So this is BU, thought of as an H space or a group, and so I can smash HG with that group, and now this object is twisted by that local system, okay, because of the construction, by construction. Of course, I have to make it equivariant, and that can be done. So taking that guy as an equivariant cohomology, specializing one of its parameters as one and all the others as groups gives rise to twisted cohomology, which recovers SLK link homology. So the twisted cohomology of these equivariant guys is SLK link homology. Okay. All right. I have 5 minutes. Maybe I can answer questions if there are any. None.
Any questions?
What I wanted to say is that there is an example of this construction recently. So there are geometric constructions of all these link homologies by various people. What you would want to do, ideally, is to take a construction that's out there, that's physical, and ask, what field theory do you start off with to recover that example? Because notice that what I have done is not specialized to any field theory, right? I just started off with an ND gauge theory on G, compactified it on a circle, and then took that compactified theory, and then took another circle with defects, and calculated my partition function for a defective tori. So what I have done really essentially is that Kovanov homology parametrizes defective tori in any ND gauge theory. That's the point I'm trying to make, is that this space of broken symmetries, whose cohomology is all these link homology theories, is the base space that parametrizes all defective tori in the sense that I've just described. So you first compactify for a circle, then you compactify it over another circle with marked points and defects, and that object is parameterized by these spaces of broken symmetries, which have Kovanov homology. So in some sense, any example you see must have some interpretation if you choose your field theory in the right way. So unless there are questions, I want to point out something recent. Yeah?
I have a question.
Sure.
So far, this works only for conjugacy classes of braids, right?
Not quite. It also works for braids. Remember I said the space BI mod T is the moduli space for braids and not just conjugacy classes? So if you write all my theorems down for the space A sub I, they also hold.
Yeah, so this gets a link invariant always.
It gets you a braid invariant for the space A sub I. So every theorem I have, just replace BI with AI, and then you would get braid invariance.
Yeah, I was concerned with more invariance, not less.
Go ahead.
For links, you are missing Markov moves, for instance.
No, you're not. I didn't want to say that. You'd have the second Markov move. It just requires you to go from UR to UR plus 1. So there is an induction process for UR spaces to UR plus 1 spaces. And if you do that, you recover the Markov second move.
Okay.
I didn't want to, muddy the waters, but yes. Remember, R was the number of strands. So you can increase the number of strands topologically by saying I take an R-stranded braid and induce up to a space with R plus 1 symmetry, just usual induction with a small subtlety that I've set aside for now.
This for UR, right?
UR gives, so if you want to talk about the second Markov move, you need to compare UR with UR plus 1, right? And I'm saying in the context of these equivariant spaces, that's simply the induction. UR space, induct up to a UR plus 1 space.
Okay.
And then, yes, then everything is true.
Thank you.
Let's make this a fully fledged question session then. Further questions for Nitu? So I have a question. So you reduced on the circle. Is that because you want to utilize the...
I wanted to get the Weil alcove. The first reduction reduced, recovered the Weil alcove.
Right.
You needed to have this symmetry data of all codimension walls because the proofs of this theorem require you to go to higher codimension walls. These are like defects that merge. There's fusion of defects that are happening.
I see.
So you need the whole Weil alcove, and you don't see that until you do the first reduction.
I see.
Then once you've got the first reduction, now you have the Weil alcove. Now you have the Weil alcove, you need the second circle to get the braid. So that's why you're actually working with tori, starting from the top down.
Sounds good. Other questions? Conrad.
So at the end, you've been talking about twistings. Can you say more exactly what kind of twistings they are and what they twist?
So they're twistings by G mod mod G, which you think of. So there are many ways to think of it. Since the real way, so you have these connections, right? BI, they map to G mod mod G add. But really, these are connections, and this is the moduli space of connections. What you really want to think of. So this is a space of connections on a circle, and this is the gauge group. So this is an equivalence of stacks, right? But really, this is the object that's physically, you're working with a gauge theory which you compactified on a circle. So this is the object that you really see. This is the way you interpret it to get, represented in terms of usual stacks, right? Smooth stacks. So if you work with this and you take the pullback, take this pullback. Now this thing has an action of the gauge group, or the loop group in this case. And now what you could do is take this and work with any space with a loop group action, any cohomology theory with a loop group action. The moment the cohomology theory has a loop group action, you can twist your cohomologies with that cohomology theory, right? This is the usual business of twisted K theory having to do with, you know the picture, I'm sure you are. The twisted K theory has to do with, the Verlinde algebra, whatever. And the way you see that is by recovering the action of the loop group and noticing that, the loop group acts on K theory. So that's really what's going on. I'm saying everything in terms of this, but really what I want to do when I twist is to pull it back here. Now see this with an LG action, enhance all my twisted cohomologies with an LG action, which you can do, and then do equivariant cohomology. And now the central charge shows up, and therefore you can twist by the central charge. So that's what the twisting is.
Okay, great. Any other questions? Okay, if not, let's thank Nitu again for the very nice talk.
I should say one thing.
Yeah.
There is a recent paper, an example of this by Rozansky and Oblomkov, where they start off with n equals 4. So they do a special case n equals 4. So remember, if you do n equals 4, you get all the way down, you get a family of objects in a 2 category. Right? If I said that this construction gives you a family of objects in an n minus 2 category, but n is 4, you get a family of objects in a 2 category. So that's a family of objects in 2 categories, a family of categories. Right? So you get a family of categories. From this, you could recover the Kovanov-Rozansky homology of these links as described by Lozansky and Oblomkov, and they start off with the 4D theory. So for them, n is 4, and their 4D theory, the one they start off with, is this Kapustin-Witten n equals 4 super-Yang-Mills theory. That's their 4D gauge theory that they're working with. So then they compactify it on a circle, and then they get all these interesting 3D theories. Those 3D theories then have defects. So then you get defective tori, and you can interpret this picture in terms of their picture that just sort of came out in the archive maybe 3 weeks ago, where they described triply graded link homology as an object that's obtained starting with defects in the 4D Kapustin-Witten theory. And you could write down exactly what the isomorphism here is to the family of categories that you get over these broken symmetry spaces. Just wanted to point out there are examples of this.
Great, yeah, this is very interesting and intriguing. Thank you so much, Nitu, again.